Hello and welcome back. For this video we'll be discussing exponential decay. There is a PDF if you'd like to print out and follow along. Exponential decay is still in the form of f of x is equal to a times b to the x. However, b here has to be bigger than 0 but also less than 1 at the same time, which means it's some sort of fractional or decimal value. The reason for that is when you take a decimal or fractional value that's less than 1 but greater than 0 and raise it to some power, the number that keeps coming out of it gets smaller and smaller and smaller. So if you take, for example, a half times a half times a half times a half, and each time you multiply it by a half, you get a smaller amount. The decay model is very similar to the growth model. The only difference is instead of having a 1 plus, we have a 1 minus the decay rate. So the decay factor is actually 1 minus the decay rate. So we're not going to increase by the rate, we're going to decrease by the rate. But everything else is still the same. We still have some initial amount that we start with, and then we decay from there. And then we have a time period, and that could be in minutes, hours, days, or weeks, depending on whatever the scenario is. Here's an example of exponential decay next to exponential growth. So on this side we have growth, and you can see as we go from left to right, things are getting bigger. And on the right hand side we have decay, which means as we go from left to right, things are getting smaller, approaching 0. Example 1, the number of acres of ponderosa pine forest decreased in the western United States from 1963 to 2002 by 0.5% annually. That's a small number there. In 1963, there were 41 million acres. That sounds like an initial or starting amount. Write a function that models the number of acres of ponderosa pine forests in the western United States over time, and that's part A. So we're going to start off with f of t, because we're talking about time, is equal to the starting amount, which was 41, and that, I'm just going to leave that as 41. I'm not going to put it in millions. I'm going to remember that it's in millions of acres, times 1 minus the decay rate. Now this is going down by 0.05%. That needs to be turned into a decimal. Now it is a decimal percent, but it's not a decimal equivalency of the percent. So that would be 0.005, and then raise that whole thing to the t power. So now we got to go ahead and simplify that a little bit. So we have f of t is going to equal 41 times 1 minus 0.005 is going to give you 0.995 to the t power. So this then becomes our function that we can use between 1963 and 2002. And part B, to the nearest tenth, about how many million acres of ponderosa pine forests were there in 2002? So we got to figure out is a time value. How many years was it between 2002 and 1963? So we go ahead and take 2002 and subtract 1963. We end up with 39 years. So our t value is going to be 39 years. So we're going to go ahead and substitute that in. So we have f of 39 is equal to 41 times 0.995 to the 39th power. And each time I multiply 0.995 by itself, and I'm going to do it 39 times, the numbers get smaller and smaller and smaller. So on the next level, we'll have f of 39 equals 41 times, and 0.995 to the 39th power comes out to 0.8224. So I'm just going to call it 0.82, round it to 0.82, and go with that calculation. Now multiply the two together, so f of 39 will equal 41 times 0.82, which is 33.62. So we're going to say that that's in, remember this is in estimate and this is in millions of acres, so we're going to say about 33,620,000 acres. Example 2, a population of 90,000 decreases by 2.5% per year. Identify the initial amount, the decay factor, and the decay rate. Then write a function that models the population over time. Okay, so our initial amount is what we started with, so 90,000. Our decay rate is 2.5% per year. But our decay factor, how much it's going down by, or what we're going to raise to the exponent, is always 1 minus the decay rate. So it's a composite. Decay factor is a composite value. So this calculation right here is the decay factor, but the decay rate, R, is this number here. So let's go ahead and write the function for this. So f of t is going to equal the initial value, which is A, 90,000, times 1 minus. Now when we go to put this decay rate in, we got to put it in as a decimal equivalency, so that would be 0.025, and then we're going to raise that to the t power. And then all we're going to do is simplify it, because this is the decay rate, and we want to turn that into a decay factor. So f of t is equal to 90,000 times, and 1 minus 0.025 will leave us with 0.975 to the t power. So we talk about the decay factor. The decay factor is actually 0.975, even though the decay rate is 0.025. And that's all they wanted us to do, is come up with a function that would allow us to calculate the amount of population over a certain given time. Example 3, you purchase a cell phone for $125. The value of the cell phone decreases by 20% annually. That's a pretty big decrease annually. Write a function that models the value of the cell phone over time, then find the value of the cell phone after 3 years. So that's a time value of 3. So 125 is what we initially bought it for, so that's our A value. So f of t is going to give us an A value of 125, our starting amount, or y-intercept. And we're going to start with 1 minus the decay rate, which is decaying or decreasing at 20%, which is 0.2. And it's over each year annually, so that's t, and t in this case is years. Okay, this is our decay rate, so let's go ahead and calculate the simplification of this. 125, and 1 minus 0.2 is going to leave us with 0.8 t. So we have a decay factor of 0.8, so it's decreasing 80%, or what's left over is 80% of the value each year. And then what we want to do now is calculate how much is actually left over after 3 years. So f of 3 is going to equal 125 times, and then we're going to do 0.8 to the third power, and that's going to give us 0.512. Now before I go ahead and multiply that, I want you to understand what this means. Since this was a percentage here, decay rate's a percentage, we're losing 20% each year, so basically we're left with 80% of the value each year. So by the time 3 years goes by, we still have a phone that's worth 51.2% of its original value. And that's what this whole calculation is doing, is tell you how much is still left over. So go ahead and multiply those together. We have f of 3 equals 125 times 0.512, leaves us with a phone value of approximately $64. So after 3 years, your $125 phone is only worth about $64.